Alright, so in my last video we talked briefly about the idea, the concept of limit, and let's quickly review it. So the concept of limit is that we're approaching a unique number from either the right side of a number or left side of this number. And so it can be calculated. Of course, we use kind of an approximation method to do it last time. And so we did kind of a table to figure out what this limit happens to be. Okay. So that now I want to kind of expand upon two ideas. So today's objectives are rather simple. So we're continuing on lesson 2.1. And I want to expand upon the idea of the limit does not exist, and I want to expand upon the formal definition of the limit. Okay. And let's make this full screen like that. Now, I'm going to get it continued. Now, in our last video, in our last lecture, we talked briefly about, this is homework assignment from yesterday, the idea of divergence. Divergence is when a function is unbounded or it's oscillated. What that basically means is that it does not approach unique number. It doesn't approach number at all. So I'm going to expand the definition of divergence to include this point. So I kind of mentioned it a little bit, but I didn't really expand upon it for you. So let's do exactly that. Let's give you another. Okay. When a limit does not exist by unbounding or oscillation. So in the first situation of unbounding, I can have a situation where my function increases like this, or like that, doesn't matter. This is y equals f of x. And it increases. So what happens is when it increases, we call this phenomena infinity. Okay, infinity doesn't mean number at all. It is the idea of increasing without stopping. Okay. And when you get to your number theory classes, you'll learn more about this concept of infinity. But for our purposes, we want to understand infinity as something where it's either increasing without bound or decreasing without bound. So this is the first situation of increasing unbounding. Okay. And to describe that point is, I would say the limit as x approaches c of f of x is positive infinity because it's increasing without stopping. What's happening? This function from both sides is increasing without stopping. Okay. Does that idea make sense? Okay. Now, the second situation that can occur is a decreasing bound. Is bounding by decreasing here. So I will put that on the next page. Here's my graph. I can have something. It doesn't have to be this shape, obviously. This is, again, y equals f of x. And this is going to be unbounded decreasing. And in this situation, we say the limit as x approaches c of f of x is equal to negative infinity because it's going down, 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 down without stopping. So that is in this situation like this concept of going decreasing without stopping. This is the negative infinity situation. Okay, this is a set of divergent problems. Now, last situation that can occur is what I talked about is oscillation. Now, oscillation is different from the other two. So something like this. Can't really draw it, but that's okay. That's, again, y equals f of x. So something like this. So something where it's repeated in this situation. This is an oscillation, or a repeating of some type. Now, when it's oscillating, what's happening is that it's not making up its mind. It's deciding between two different points. And this is a problem, is it not? When I have it when it's going between two different points, I cannot, it has to go towards one number. It cannot go towards two. So I can give you example. It's kind of really hard for me to draw it out, but I tried my best. So deal with it. In this situation, I do not say the limit approaches infinity because it's not. It's oscillating between two different numbers. Positive number here, negative number there. In this situation, I say the limit does not exist. Okay? So when it's oscillating, I say the limit as x approaches c of f of x does not exist. And why do I say that it does not exist? Because it's not, we don't know exactly where it is going. You see, it can be approaching it approaches two different numbers. And because we don't know exactly where it is, this is why we say it does not exist. Okay? Everybody gets it? Yeah. Let's do some examples, kind of a visual, how to work with graph before we get into formal definition of limit, which is on next page. So our example here it is determine the limit of f of x at the following. This is 1, 2, 3, 4, 5. This is 1, 2, 3, 4. This is going to do y equals f of x. Okay. So let's do A. The limit as x approaches 1 from the right of f of x. B. Limit as x approaches 1 from the left of f of x. C. The limit as x approaches 1 of f of x. Letter D. The limit as x approaches 3 of f of x. Okay. So we're doing this by visual inspection. So I'm going to try to look at the graph and best describe what I see. So for first problem, we're simply approaching it from the right side. So approaching 1 from the right, which is approaching 1, which is approaching from this way. So like this, you can see that it's approaching our -1 right here. Okay. I can't, as I said, my drawing isn't perfect, but it was working. So it's approaching -1 from the right here, kind of visually speaking. Yeah, it's kind of a visual guess when I'm looking at it. And then to approach it from the left side, in this situation, approaching it from the left, which is coming this way, it's approaching 0. Okay, it's approaching 0. And then, so what do I say about the limit of f of x? These two have to be exactly the same for a limit to exist. And since they are not the same, this limit does not exist. So write it like this, does not exist. Now, same thing for 3. Alright, as I approach 3 from the left, here, I am approaching 1. So I'm going to break it down. Limit as x approaches 3 from the left is equal to 1. And then from the right, which is coming this way, it's approaching 4. Which is 4. So again, I can see that in this situation, the limit does not exist because these two are not exactly the same. That's the idea behind limits not existing. They have to be exactly the same. Of course, this is something I mentioned in previous video. In previous point, the idea that the right-hand limit and the left-hand limit must be exactly the same in order for you to have limits. Now, so that gives you kind of an idea of what we're talking about when we speak of a limit that does not exist. It's approaching two different numbers. It's approaching two different numbers when I talk about limits that does not exist. Okay. Lastly, I want to do an example of an infinite limit, and then we'll move on. And then we'll move on to formal definition of limit, and then that'll be done. Now, lastly, my next example let's see. determine the limit as x approaches 0 of 1 over x to the fourth. Okay. Now, you guys have graphing calculators, which I'm sure that you guys will be more than happy to use, and this is what we'll do, since I'm lazy and do not feel like using the actual methods to graph it for you. We'll want to graph this limit firstly. So let's graph this function. And since it is, of course, x to the fourth, let's get 1 over x to the fourth. Let's graph this function. Okay. You guys have fancy graphing machines. You guys know how to use those. You guys are smart. I have my own calculator which follows its own rules. So we graph this function, and this is something very steep graph like this. Okay. It looks like that. Now I can kind of determine this by my visual inspection. My visual inspection here. I see that when I approach it from the right, limit as x approaches 0 from the right of f of x, then this is going to be y equals 1 over x to the fourth, which is equal to f of x. Okay, now I'm approaching it from the right, coming this way. I see it's going towards positive infinity because it's increasing without stopping once again. So it's positive infinity. Limit as x approaches 0 from the left. Same concept, same thing. This is minus, this is plus. And it's also going to negative infinity. Positive infinity, sorry. It's positive infinity. And since they're both increasing towards the positive infinity, I therefore, as a logical extension, must state that the limit as x approaches 0 of f of x, or 1 over x to the fourth, is equal to positive infinity. Very important that you write the positive sign, because it is not assumed that you're increasing when you don't note the sign. So positive infinity is something that you need to put down on your paper, so it's very clear that it's increasing without bound and without situation. Alright, so therefore, this is the idea. Okay. Right hand limit, left hand limit must be the same, and then you have limit. If you don't, then it does not exist. Plain and simple. Okay? So now, let's move on to formal definition of limit, which will take us the majority of the section. And it's not really as difficult per se, but it's okay. So when we talk about formal definition of limit, I mentioned in our informal definition, what did we talk about? Approaching numbers from two different points, from the right side and from its left side. The formal definition makes precise what this idea, this concept is. So when you write it, so when you see this, please bear with me. It's basically formally telling you what I've just told you. It's formalizing this in such a way where we can be precise about it. Okay. So it says, the formal definition is as follows. Let's use a green pen. it says for every. This is the symbol upside down. A means for every, as you recall from last lecture. It means for every epsilon, Greek letter, greater than 0, there corresponds a delta greater than 0 such that, and in my notations from this point forward, it will be ST for such that. The absolute value of f of x minus L is less than epsilon whenever whenever 0 is less, whenever x minus c is greater than 0, but less than delta, like that. Okay. There's this formal definition of a limit, and it sounds really complicated. This is often called delta epsilon definition of a limit. Delta epsilon definition of a limit. Alright, so I'm going to draw a picture for you guys to help you guys visualize what I'm talking about. Okay. So let's increase it to another page. Let's change the pen color. Okay. So here's my graph. So here's my graph of f of x. So the idea is that the limit is at this point. This is going to be my L. And then let me choose a different color. Let's say red. Here. Between here and here. And the distance between here and here is epsilon. So the idea is that epsilon corresponds with the y-axis. Okay. So when I'm talking about, so in the first part of my definition here, such that epsilon is greater than 0, it corresponds with the y-axis. So I'm speaking about y-axis in this situation. Okay? Now I'm going to use the color purple. Okay. And in the same situation, oops, let me get back to black here. This is our letter C, because that's what we're approaching. And then we have purple, we'll use like that. And the distance between here and here is delta. Okay. So the idea is that we're approaching it again from right and from left. Okay. the idea is that we're saying is that if there's an interval delta, I'll write it right here, delta corresponds with x-axis. The idea is if there's an interval on the x-axis, there's an interval on the y-axis. And the converse is true. If there's an interval on the y-axis, there must be an interval on the x-axis. So the idea here, I'm going to put this in normal English. If there is interval on x-axis, there is interval on y-axis. Okay? Now, it seems like a very complicated concept. It's really it's a very straightforward thing. Now, when I took calculus, we didn't really learn this, but I taught myself how to do this. I learned this later on in my other calculus classes that I took. So, the idea is to give a precise definition to what I'm speaking about. And why I'm giving you this now, because in the next section, we'll talk about algebra, how to calculate limits using algebra, and I want to have an idea of what the hell I'm talking about before I do anything. Okay? Alright, so let's do an example of a delta epsilon limit to show you what the hell I'm speaking about. So we're going to use the delta epsilon definition of a limit to show the limit as x approaches. I don't want to do the one out of the book. Let's do it the time. As x approaches 2 of x plus 3 is equal to 5. Okay. So that's what we're going to do here. Now we need to set this up. So we have for a solution in this situation Alright. The first thing we want to do is set up the idea of f of x minus L. We want to set this portion of the limit up first. Okay. Everybody see that portion? Here. So we set up this absolute value. And so the way we do that is by moving this. We define this to be our limit, and we define this to be our f of x. So it's going to be absolute value of x plus 3 minus 5. That's L, and that's f of x. Alright? And then, what we want to do after that is, of course, simplify it And since we're all arithmetic majors here, we can say this is x minus 2. Alright? So everybody follow how this worked. I first set up the function, subtract from our defined limit, or assumed limit actually. Okay. So we take the function, subtract limit. Okay? Now that I have done that, this function minus the limit is what is less than our delta. Okay. So this is less than delta. Okay. Recall that from my definition of limit here. Alright. So you see here, we have x minus c is less than delta. How did I know to make that less than delta instead of epsilon? Okay. The reason why I knew to make it delta instead of epsilon is because it comes out to exactly x minus 2. Okay, you see that? So since it comes out to, this is, in this situation, this is x minus c. That's how I know to make it less than delta. Okay. Okay, so when it comes, so we make that less than delta, and not epsilon, because that's we're using our definition here. So now I know that x minus 2 must be less than delta. Now, in this situation, I have to choose an epsilon. Okay? So in the second part, I have to choose an epsilon. That's greater than 0, obviously. So, in this situation, what do I want to choose for it? Okay. So I'm simply going to choose let delta equal epsilon. And you may ask, how did I know to do that? Well, in this situation, there's no number that's out in front. If this is 1, then you make it 1. If this is a 4, then it would be epsilon divided by 4. Okay. That's how you know what to choose for your epsilons, and we'll talk more in detail about that later. So I'm going to let my delta equal epsilon. Thusly, as such, I can therefore say absolute value of f of x subtracted from its limit is equal to the absolute value of x minus 2, which is less. Which is less than delta, which is equal to delta, which is equal to epsilon, which is equal to epsilon. So everybody got it, kind of the idea. The idea is that we're defining a region so that we can show this to be true. Okay? Okay, everybody understand this? There you go. Alright, very good. Now let's do another one of these just to kind of get us into the flow of things. So we'll use delta epsilon form of this to show it. And once again, our solution is, of course, to firstly define my f of x minus L. So this will be 3x minus 3 minus 0, which is equal to 3x minus 3, absolute value. And then that will be less, well, not less than anything. So now I see that the 3 is in common, so I want to factor out the 3. So if I factor out the 3, this becomes 3 absolute value of x minus 1 less than delta. Once again, this is x minus our c, which is 1. Our c, which is 1, and so that's the idea. That's why we make it less than delta. Now, to prove that this is true, I have to, of course, choose an epsilon. Once again. So this x minus 1 becomes delta. So we're going to choose epsilon. So we have 3 times delta is equal to epsilon. And I want to show that this is true. How do I do that? By making delta into epsilon divided by 3. So this becomes 3 times epsilon over 3 equals epsilon. That kills that. So I get epsilon equals epsilon, and this is a check, and this is a proof. Okay, it's kind of circular proof, so to speak, but it helps us to define what a limit is. Now, I promise you on your exam, you'll only have to do one of these, because these are pains in the butt and nobody likes to do them. So, the idea with delta epsilon is to formally prove or to show that the limit really does approach this particular number. Okay? And so now that I've gone over that, I'm not going to have you do one where the limit doesn't exist. So I don't want you to do the ones that involve limits non-existing because that's still painful, and I don't feel like grading them. So therefore, I want you to do for your homework problems. So I want you to read the rest of the chapter, or I just want you to read the entire chapter of 2.1, which starts on page 55, page 50, goes all the way to 58. And since yesterday you did numbers 1 through 9, you're going to do on page 59 numbers numbers 11 through 16, and then number 18, 20, and 21, and then
see what I want you to do here. Determine the limit. Okay. I want you to try numbers 29.
And I want you to try, and then after that,
I want you to do
29.
then do then do 50 through 54 evens. And then do
50 to 55, actually. Okay. So that's all homework I want you to do for this section. And if you have questions, feel free to ask them. And the solutions will eventually be posted. I just have to sit and do them. So in next section, we'll talk about algebra and avoiding all of this mess of approximation. Okay. And the whole problem with doing our limits by this method, it's kind of risk-taking. I don't have precise certainty to it. So in this next section, we'll learn about the algebra of limits
and how we don't even have to do any of this delta epsilon stuff and any of this things like that. Although you can, but why would you do that? So we'll do that next time and we'll cover a lot of things. Alright?